This video outlines the background of the CAPO-Test, the cut and pull-out test for compressive strength of concrete in place, and gives the details of the operation of the system, step by step. For maintenance and check of the equipment, the user manual must be carefully followed. Performing the CAPO-Test starts out with coring a hole, 18.4 mm in diameter 65 mm deep, then the surface is planed, and a recess 25 mm deep is routed 25 mm in diameter. An expansion tool with a folded steel ring is inserted in the cored hole and expanded in the recess to 25 mm diameter. The pull bolt is coupled to a precision hydraulic pull machine and loaded to failure of the concrete between the expanded ring and a counterpressure 55 mm inner diameter placed centrally on the surface. The yellow arrows indicate the compression forces between the expanded ring and the counterpressure, and the red dotted lines the final failure. The pull-out force is correlated to compressive strength by cylinders, cubes or cores by means of robust, general correlations. Typical CAPO-Test failure. Note the cracking indicated by the white arrows. These cracks are caused by the compression in the strut between the expanded ring and the counterpressure. They are sliced after the peak load has been reached. The CAPO-Test is the most accurate test system for in-place strength available today, covered by ASTM C900, European norm EN 12504-3 and British standard BS 1887-207, and can be used with great confidence on all types of normal concretes without correlation to drilled-out cores. For a trained operator, one CAPO-Test takes about 15 minutes. All equipment is portable, there is only minimum damage to the structure that can easily be repaired, and the test result is immediately available. Water and electricity supply are required. The property measured, the pull-out force, is related directly to compressive strength. That is why robust, general correlations exist between CAPO-Test pull-out force and standard cylinder, cube or core strength, verified during the past 40 years in many correlation programs worldwide. All concrete parameters have been investigated, such as different cementitious materials, water-cement ratio, age, air entrainment, curing, admixtures, depth of carbonation and type, shape and size of aggregates up to 40 mm. The use of lightweight aggregates, however, produces a significantly different correlation. For testing on site, the ACI Technical Journal, Technical Paper No. 113M76, reports from testing of 15 bridges, 25 to 52 years of age, ranging in strength from 15 megapascals to 50 megapascals. On average, the compressive strength estimated from the CAPO-Test was 2.8% greater than the measured core strength when the general cube correlation is followed. This is despite the concrete tested was carbonated up to a 50 mm depth.
The complete set of CAPO-Test equipment consists of the hydraulic pull machine C104 having a maximum load capacity of 100 kN, a drill machine for coring and planing, the preparation kit C101 and a suction plate with vacuum pump C102, the SV kit. Before testing, make sure all parts are available as shown in the CAPO-Test manual. The C101 preparation kit contains the coring unit, the diamond planer unit, the recess router, the expansion tool with counterpressure and coupling, a water pump and various keys for performing the testing. The reinforcement is located. The supplied detector can be used up to a depth of approximately 70 mm, otherwise a cover meter must be used. The reinforcement must be at least 10 mm away from the failure zone. This small distance makes the CAPO-Test applicable even in highly congested reinforcement areas. The test location is selected in the middle of the reinforcement mesh.
The system can be used with and without a suction plate. The suction plate is recommended on even and smooth concrete surfaces. Using the suction plate controls accurately the initial 3 steps: coring of the center hole, planing of the surface and routing of the recess. Otherwise, the 3 steps are performed holding the equipment by hand, as later described. The clamping pliers are attached to the suction plate, loosely, and the plate is connected to the activated vacuum pump. Pressing the vacuum plate against the surface will pull the vacuum to approximately -0.8 bar indicated on the plate's vacuum gauge. Install the diamond coring bit on the shaft of the assembled coring housing. The green coring bit produces the required coring depth of approximately 65 mm. Alternatively, the red coring bit may be used followed up the green coring bit. Unthreading the coring bits from the shaft is easily done by means of two keys. A 19 mm key positioned on the recesses at the top of the shaft and a 17 mm key at the coring bit's barrel. The green coring bit could be too long depending on the height of the suction plate after initial suction. Start out with the red coring bit, and terminate the cord hole with the green bit. The drill unit is positioned in the vacuum plate and kept firmly attached by the adjustable clamping pliers. Make sure the shaft attached to the coring bit can turn easily. Attach the water plastic hoses to the drill unit, inlet hose to the top nipple and the wastewater hose to the bottom nipple. Connect the inlet hose to the water pump and submerge the pump in a bucket with water. Connect the drill machine's chock to the top of the coring shaft. Do not use the drill machine's hammer option when coring. Such hammer drilling will ruin the diamonds on the coring bit quickly and cause cracking in the concrete. Activate the water pump. The water must run through the coring unit and back into the water bucket. Coring takes place to full depth. Retract the drill regularly and make sure the water is flowing freely through the system. Watch the wastewater color. Retract the coring shaft fully and remove the unit, deactivating the clamps. Break the core with a screwdriver and remove it with a tweezer. The core is excellent for testing the depth of carbonation, for example by spraying its surface with the rainbow indicator or the deep purple indicator. Mount the diamond planing wheel in the planing device. Attach the water hoses to the device and clamp it into the suction plate using the adjustable pliers. Make sure the shaft can turn freely. Attach the drill machine to the unit's shaft and plan the surface to a depth of 3 to 4 mm. Stop the water circulation and remove the device. Attach the inlet water hose to the recess router machine, insert the diamond router in the cord hole and route the recess at 25 mm depth. Make sure the flange of the router is pressed all the time against the planed surface. Move the flange in bigger and bigger circles until it follows the 100 mm inner diameter of the cavity of the suction plate. Use 2 sets of fingers to press the flange against the planed surface. The milling of the recess is done quickly, in 5 to 10 seconds. To disengage the vacuum plate, disconnect the vacuum hose from the vacuum nipple and press a small screwdriver against the bottom of the nipple.
Without the use of the vacuum plate, the 3 initial steps are done as follows. Attach the red diamond coring bit to the coring unit as well as the water hoses similarly as illustrated previously. Core first to half depth, remove the core in pieces and continue coring to full depth. Break the remaining core and remove it by the tweezer. Assemble the planing unit and insert the brass centering piece in the center hole of the diamond planer wheel. Make sure the brass piece can turn freely. Insert the centering brass piece in the cord hole. Connect the drill machine to the shaft as well as the water supply hose to the unit. Plane the surface to a depth between 2 and 4 mm. The recess router is prepared. Check the depth to the diamond bit to be 25 mm from the flange using the 25 mm distance piece supplied in the preparation kit's tray. Connect the water supply and route the recess in bigger and bigger circles until the flange follows the plane surface outer 100 mm circumference. Press all the time the flange with 2 sets of fingers against the flange. The expansion tool components consist of the folded insert ring C112, the cone pull bolt, the base pull bolt, the nut, the sliding disc, the counterpressure and the capo coupling. To assemble the expansion tool, first insert the C112 folded insert on the cone pull bolt. Make sure the inner sharp edge of the insert is resting against the cone, not the beveled inner edge. Oil the cone slightly. Then thread the base pull bolt fully into the nut. Install the sliding disc on the nut's neck and thread the cone pull bolt, left-hand thread, fully into the base pull bolt. During this operation, hold the base pull bolt at its end and thread the cone bolt fully into the base pull bolt. It is important to hold the base pull bolt. Note: do not hold the nut, as the threading of the cone pull bolt into the base pull bolt may unthread the base pull bolt from the nut. The expansion unit is now prepared properly with no travel of the insert on the cone pull bolt. Insert the unit into the cord and recessed hole, ready for expansion of the insert. Note: do not keep the nut in the same position and turn the base pull bolt. This will only fracture the neck of the nut. Hold the base pull bolt in the same position with the adjustable wrench and turn the nut with the large 46 mm key clockwise, 9½ rotation until hard resistance is felt in the base pull bolt's top thread. Colored yellow is emerging. Back off the nut slightly. Install the counterpressure with its flat surface against the plain concrete surface. Thread the capo coupling 2 complete threads on the base pull bolt, making sure the 3 small pins on the coupling are pointing against the concrete surface. Activate the hydraulic pull machine by extending fully the telescope handle. Couple the capo coupling to the pull machine. Make sure the coupling is fully engaged. Remove the slack between the pull machine front surface and the counterpressure by turning the instrument clockwise. Activate the green button on the instrument's gauge. Press it until 0000 turns up. Release it and activate it again, shortly. The gauge will now show 0.0 kN indicating it is ready for testing. Turn the loading telescope handle slowly clockwise with a uniform speed. One pull-out test has to last minimum 15 seconds. The rate of loading should be about 2 to 3 seconds per turn of the handle, so go easy, and hold the instrument's pistol shaft with the other hand. Keep on loading until the maximum pull force has been reached, then turn the handle quickly clockwise to release the pull-out cone. The peak load will be shown on the gauge with an H in front. In this case the peak load is 34.0 kN. The peak load is saved in the instrument's memory with date and time of testing as well for later printout and documentation.
The load displacement curve is only shown for illustration purposes. Note that the curve is similar to the curve from testing compressive strength of standard laboratory specimens, clearly consisting of three parts: linearity, compression of the strut between the expanded insert and the counterpressure, and the softening regime producing the final pull-out cone. After the telescope handle has been loaded fully, the failure cone is extracted and inspected. A proper performed CAPO-Test has, as with the lock test, to show a sharp edge on the concrete surface from the inner 55 mm counterpressure ring, and the depth to the expanded insert must be 25 mm. Uncouple the coupling from the instrument, then unthread the coupling from the base pull bolt and remove the counterpressure. Note the cracks in the extracted cone. They are formed in the softening regime, where the parallel cracking in the compression strut is sliced between the outer ring edge and the inner counterpressure ring. The expanded steel ring can be compressed again using a C111 resizing tool set and reused 2 to 3 times before it breaks. The maximum pull force is written on the concrete surface in kilonewton and correlated to either standard cylinder strength or to standard cube strength in megapascals or psi. Using the instrument's calibration table, the compressive strength can be obtained relating the calibrated pull force to strength on standard cylinders or cubes, following the general correlations. To dismantle the expansion unit, use two 14 mm keys. Extract the cone and disassemble the parts. The expanded steel ring on the cone pull bolt is removed by light striking, the parts cleaned and oiled slightly, and assembled as shown previously. To repair the cone hole left in the concrete, apply a non-shrink mortar. First, spray the surface slightly with water, then mix the mortar and press it into the hole with a spatula. Smoothen the surface. To document the values obtained, the Amigas software is used. Install the software in a laptop and connect the supplied cable to the pull machine. Follow the Amigas software manual after PO is shown and the read date window activated. The peak load is shown with the test's date and time.
Feel free to contact us for any question referring to this test system and the others we offer, at our offices in Copenhagen, Denmark as well as in Chicago, Illinois, USA. You are also welcome to visit our website for more information. On Garmin Instruments we thank you very much for your attention and we stay ready to answer any question.